Okay, so today I want to talk about the Christoffel symbol. That's specifically, so we're going to be calling the Christoffel symbol something called intrinsic curvature. Okay, or extrinsic curvature. The Christoffel symbol is really going to tell us something about the curvature of the spacetime. So just to reiterate what our picture is so far is we have some space. This is sort of our three-dimensional manifold or n-dimensional manifold, and at every point in space here, we have these little machines. Right? We have, well, not only do we have these little machines, we have a whole world of objects, mathematical objects that we have at our disposal. That we sort of came to these objects through some mathematical intuition, where we say, I like to call it the what's stopping us syndrome almost. It's we say we know we have these objects F, mu, and then we rationalize and we say, well, nothing's really stopping us from saying that we could have these other objects. Write this a little bit better. E mu. Right, so these are contravariant vectors, and these are covariant vectors. So to give them the vector notation, and then we also have these G mu nu guys, G mu nu, and these are our contravariant covariant metric tensors, and these things are maps, right? So you could sort of think of these things as maps that take these guys to real numbers, right? So this guy will take this world of covectors and spit out a real number, and this guy will do the same here, and it'll spit out a real number. And these real numbers are things that are at our disposal too. So these things are things that we could put in this little space as well. And so we have objects, we have mathematical objects that exist at some point, and we have these little machines that exist at some point. Right? They're kind of like operators. Right? And this is good. This is actually a very important notion, that these things can be thought of as operators, as taking mathematical objects and converting them into other types of mathematical objects. That's what operators do. Like a derivative can take a function and output another function, right? It doesn't necessarily, these machines, again, they don't necessarily have to operate on just these guys. We saw earlier that G mu nu can just operate on E mu. And instead of outputting a real number, we output an F mu, or some sort of contravariant object. And we saw sort of the brunt work on how this happened. Right? And again, these guys have a basis. E mu, tensor product E nu. And these guys had a basis as well. This would be E mu. And by doing all this work, we found out that we come to this answer here. I won't erase that. Okay. But here, so today I want to. We haven't really gone over this yet. This is the tensor product. I kind of just sort of told you that this is just the tensor product, and we kind of moved on from there. But we will go more into that, right? But today I thought, let's go over the Christoffel symbol. So Christoffel symbol. I remember I read a meme somewhere that said these are just Christoffel symbols. Because they don't transform in ways that we would want them to, right? So we're going to find out that Christoffel symbols are really important, and they're essential in helping us keep a tensor. If we had some tensor t mu nu, and we want to take the derivative of this tensor, and we want to tensor back, say, e mu nu, we need to invoke the Christoffel symbol in this, because if we don't have the Christoffel symbol, tensors are not going to be able to be translated into tensors through differentiation. Functions can be translated into functions through just straight up differentiation, but tensors won't, and we need this Christoffel symbol in order to do this. So let's define exactly what the Christoffel symbol is. The Christoffel symbol, in its most fundamental form, I'll make this a little bit better. So the Christoffel symbol in its most fundamental form has 3 indices on it. We'll say I, J, and M. And it's equal to, we're just going to define it. And we're going to say it's equal to E, I, actually, to make it even more, actually, I'll just go like that. I'll just do like that. So U, J, E, M. This is how we define the Christoffel symbol. So it's the derivative of the basis vector with respect to another basis, right? And we could sort of see this as we're traveling along some line and we have some vector. Along this line. And as we travel along this line, this vector might look like this as we travel along this line. And this vector, again, lives in some orthogonal space. Right? This vector lives in some orthogonal space like this. And the Christoffel symbol kind of takes into account, you can sort of think of it as this thing that takes into account the change in these basis vectors with respect to the change in the components of the function that defines our space. All right, so this is how we're going to define this thing. Okay. So I will sort of box this like that. So this is our definition of the Christoffel symbol, right? And it's in a certain direction. It's in a certain contravariant direction here. This EM. So just as an example, to make this a little bit more tangible, the Christoffel symbol 1, 0, 2 is going to be equal to D, E, this is going to be 0, so there's 0th component, or 0 basis vector, U2, E1. So this thing itself almost has a basis. This is the direction we're in, and this is the component, the 0,2 component in this in the E1 direction. Okay. So the Christoffel symbol, again, it's sort of this esoteric. Picturing it is kind of difficult. What I would say is that we just define it like this, because when we define it like this, we are going to come to equations like the geodesic equation, for example, in which this is going to show up. this is going to show up, and so we'll be able to replace it with this. So I want to start off by considering Gij. We're going to go over intrinsic curvature first, the intrinsic curvature formula. So I'll actually write this down. Intrinsic curvature formula. There we go. And the intrinsic curvature formula is a formula that'll tell us what this guy is in terms of Gij, right? So in terms of Gij. The reason this is called the intrinsic curvature formula as opposed to the extrinsic is because we make reference to Gij. And if we remember, Gij is this thing, it's this little tiny machine that exists, it's embedded within every point in space, right? And what this is going to help us do is it's going to help us say, it's going to help us do this. We have some space, and we have a point embedded in that space in which we have Gij, right? And if we can get an intrinsic curvature formula for Christoffel symbols, this will allow us to say that inside this space we have Gij along with all of this other stuff, and and our Christoffel symbol, right? Ij, for example, right? That this is what the intrinsic curvature formula means. It means that for every point in space, we also have a Christoffel symbol, or we can calculate Christoffel symbols for every point in space. Okay. So let's begin the derivation. So Gij, if we remember, is just merely, it's got its basis is Ei, Ej. And if that's its basis, we could take the derivative of Gij. So the derivative with respect to mu, or we'll just say uk, with respect to some direction. K can take on values 1 to 3, or 0 to 3. If we're dealing with space-time, Gij. And this is equal to the derivative. We'll just do the same thing to the other side. uk times Ei Ej, like that. So far, so good. We've just taken derivatives of both sides. And now I want to consider what something like this might look like. Duk Gij. So we just calculated that, but I also want to consider plus Dui, or Duj. Let's say J here. My pen's starting to bug out a little bit. Gki minus Dui Gjk. So what does this equal? Okay, so this equals, I'll actually erase the question mark now. So this thing equals, we can do this whole thing out. So the derivative of this, well, as we've seen, actually we didn't see yet. I'll write this out. So we're going to do the chain rule on this right here. So we do the chain rule. What we get is d duk times ej plus ei times the derivative of, actually, wait, hold on. I'm missing something here. I need to put an ei right here. So I'll just redo this really quick. So we have the derivative of ei, d with respect to uk, times eij, or ej, plus ei times the derivative with respect to uk of ej. Okay, and we can do that for this guy here too. So if you see the pattern, it's going to be ek with respect to ui times ei, a little hat on a, like that, and then ek, like that, dui of ei, like that, and then plus dui, this actually should be a j, so I'll just make that a j. This is a j, and this is an I, and then ej e hat k plus e hat j times d ei with respect to k u k. Okay. So what we'll see here is this guy here and this guy here. Well, we will be able to cancel that out because this is going to be, if I accidentally missed a negative here, because we look at this negative here. So this right here should be, these two guys should be negative, right? And so with that being said, these two guys in green are going to cancel out. And then I'm going to also be able to cancel out this guy with this guy. And what we end up getting is this right here plus this. Well, these two are the same thing. And these two guys are kind of the same thing because we have, if I just were to, let's see here. This would be equal to d e j. Actually, this would be eij, or ei times d e j d u k plus ei again, dek duj. My pen's bugging out again. duj. All right, well, these two guys are the same. These two guys are actually the same thing. We have a little bit of swapping of indices, but nevertheless, these two guys are the same thing, and we get that this is 2 times EI times DEK, because this is just a basis, the basis with respect to another basis. So we can condense this like this. Okay. All right, so I'm going to take this actually over here now. Bring this all the way up here. So I'll just say, okay, copy it. 2di dek duj, like that. All right, well, we said that this guy right here was a Christoffel symbol, right? This guy, that's what our definition of the Christoffel symbol was. So with that in mind, if we define the Christoffel symbol to be this, and this is equal to this, remember this right here, this shortened condensed guy is actually equal to this guy right here. So I could actually say, erase this arrow really quick, and I can say these two guys are equal. I did this calculation and I found out that these two guys are equal. So if I were to divide this by 2, so divide it by 2, and then raise the I index, right? Raise the I index with, we saw in an earlier video that we can raise indices with the metric tensor. If I did this, then I just put all this in here. This is 2EI times DEK DUJ. All right, well, this guy is the Christoffel symbol, and then we're summing over I, right? And the 2 here will cancel out with this 2. So, but then if this here we said was equal to this, so in a sense, if we just keep this 1/2, keep the ij, and then just replace this with this right here, we get duk gij plus d duj gki minus this guy right here, d dui gik, like that. Well, okay, we said that this right here was equal to this, right? And this right here is equal to this. JK, like that. So that means this is equal to this right here. So our intrinsic formula for our Christoffel symbol MJK is equal to 1/2 G mi times, now I'm going to write this a little bit differently to condense it a little bit. G I j comma k plus g k I comma I. Actually, that should be a j. Actually, I'm messing that up. That should be those should be the opposite. So this should be an I. My pen is bugging out again. This I comma j minus I k comma j. And this right here is our intrinsic formula. Right, so we see we have this metric tensor. We're just summing over different indices. They're all the same metric tensor. We're just rearranging some of the indices around, and then we're summing over some of them. Right, we're summing over i's, because we have an I here. We're defining our j values, we're defining our k values. So in essence, we're really only summing over i's in this, right? Because we've already defined j and k's, and we have i's. And then we also have this m. We gotta deal with the m here. It means we're summing over those as well. Or actually, no, we actually define the m's too. Right. So here if we define j and we define k and we define m, all we have to do is sum over i's. Right. So our i's show up right here, and right here. And so thus we have the picture. We have this picture. We have our space-time, and we have our g mu nu. We just replaced mu and nu with I and j. And this ultimately leads us to, all right, well, if we sum, so these are the two things we define, and we only have to sum over mu, right? So this is going to be mu nu, and then m. So this is our intrinsic formula. Intrinsic formula. Right. And so the next thing we want to do is, okay, well, what's the extrinsic? What's the extrinsic formula? And that formula we're going to go over next. Okay. Before I end this video, again, I just want to reiterate, we have this picture, we have this g mu nu now, and from the g mu nu, if we take derivatives of it, we can get our Christoffel symbols, or this is also sometimes known as the affine connection. What we'll see is that the affine connection plays a big role in many formulas. The geodesic and the covariant derivative. So this is a very, very important object. And again, it is located, there is an affine connection that exists everywhere in space, at point P, at point Q, at point R. We could say this is point T. There is an affine connection at every point in space. And we could say, well, okay, this thing shows up in the covariant derivative. What this actually is, the reason it's called an affine connection is because it serves as a connection as we move along two paths in space. As we move along here, if we assume that this is some small value, this affine connection is going to give us the connection between a vector, say, that lives right here. So say we have a little vector right here that lives. This is a little bit of a misrepresentation, but say we had a vector here, right? And we had a vector here, and the relationship between the two vectors is given by this. Right? We want to know how this changes as we go from point P to point R, or from point P to point Q, or from point P to point T. We could travel in this direction right here. But we wanted, so this guy is central importance, and understanding that. And we'll get into why that's the case. But just keep in mind that the Christoffel symbol, or the affine connection, is a really, really important object. And then later we'll actually get into that we have the affine connection. And we have this interesting object here. Which is the spin connection. So affine connection, and the spin connection. The spin connection is going to connect us. Say we have, well, I'll get into more details on this in another video. I don't want these videos to go on too long, but say we have, for example, we want to measure something in our three-dimensional manifold. Right? We have a little laboratory, and we want to measure. We want to make some measurements. So, well, the only way that we can make measurements, and I have to go into a few more things to actually go deep into this. The only way that we can make measurements is if we set up an orthogonal basis system. Okay. And so the connection between the basis in our manifold and our chosen orthogonal basis is given by this guy, is given by the spin connection. This is where interesting physics begins to take hold. And before I actually move on, I wanna really introduce this kind of stuff because this came to me as an interesting sort of revelation. When you set up, so we have some space. When you set up an orthogonal basis system, we typically think of this orthogonal basis system as being constructed of basis vectors in orthogonal directions. But we can generalize what is orthogonality. What does orthogonality actually mean? Because we can have functions that are orthogonal, such as in the Fourier series. Functions can be orthogonal. Vectors can obviously be orthogonal. Vectors, not vectors. Vectors can be orthogonal. Matrices can also be orthogonal, like the spin Pauli matrices. Right? If we multiply, or perhaps not the spin, I can't remember exactly what happens when you multiply the spin Pauli matrix, but nevertheless, we could set up a basis system in which matrices, we can set up an orthogonal basis of matrices. Right? So, we could set up systems in which the basis could be functions. That's functional analysis. Vectors, that's vector calculus. Or matrices, and that's abstract algebra. Lie spaces and stuff like that. Again though, the thing is, when we set up this basis system, when we set up this basis system, we have an orthogonal basis. But when we have an orthogonal basis, we can link this to our spacetime with the spin connection. Now, why is it called a spin connection? Well, because oftentimes physicists are interested in what the connection is between GR and quantum. And this here is going to play a big role in quantum gravity. Because again, I'll just reiterate this one more time. Matrices, these guys can act as bases for states, for quantum states. Vectors can act as bases for quantum states. If we were to think of these things as representing, for example, wave functions. A wave function, this can also, again, wave functions can be, they're functions, and if we have a set of orthogonal wave functions, then we have an orthogonal basis, and if we have an orthogonal basis, we can connect this to our spacetime with the spin connection. Right, so the affine connection, this is important. This is going to help. This is going to tell us how vectors travel along our three-dimensional manifold, or d-dimensional manifold. This is going to be important. But the spin connection here, this is going to be our link to the real world, our connection to the real world. So this is a connection in GR. This is our connection to real world and a lot of the introduction to quantum gravity and stuff like that. And with that being said, I'm going to leave you on this big giant hanger note here. With that being said, I will stop the video and I'll see you in the next one.